Welcome to my channel, Dr. Munshi Nasser Skillton. How are you, my dear learners? In this video, we are going to talk about all the chapters of econometrics that you need to understand for your research purpose or for your academic purposes. So these chapters are immensely important. All the statistical tools and technique that we use for our research purposes, from economics, from business, from science, from any other domains, you can easily apply these techniques, and these techniques are applicable for statistical analysis and of course econometric analysis. On top of it, in this particular video, I'm going to share the book that I'm going to follow, the Gujarati Econometrics by Example. This book and its solution manual of all the exercises will be given in the video description box so that you can easily understand the solutions and work by yourself. So without wasting any time, let's get started. My dear learners, the first chapter that we are going to talk about is the linear regression model. And this is the first model any econometrics book starts with. So this book has already started with this general form of linear regression model. In other words, we say LPM. And as you can see over here, there are two important things in this particular case. Number one is the dependent variable, and also number two is your intercept and different type of coefficients. So these are the coefficients which are available in a linear regression form. In short form, we use yi equal to bx plus u. Here yi meaning the dependent variable, b is the coefficients, x is the independent variable, and ui is the error or random error or randomness. X is the regression, x is the vector of regressors, and y is an error term. So this is the basic fundamental model of any linear regression model. Any linear regression analysis, you start with this model, and we will proceed with ordinary least square model after the linear model, and we will see all the assumptions that it is required to check for a good linear regression or ordinary least square model. Gradually we will discuss about other important aspects of econometrics in this whole econometric video in less than 20 minutes time. So the next one is the population of true model. The equation is known as the population or the true model. Here the true model meaning that without the head over here, the model is called as a population or true model. Okay, and we always try to make a sample model or estimated model close to the population or true model. So here all the information that I just shared, all these informations are given in more detail. You can just have a look one by one. Now simple regression function is the same way we are showing in the linear regression model. This is one that we are talking about, and the most important part over here is the estimated one. This is the estimated model we are talking about y hat. This is the estimated model. Estimated model meaning that it is the representation of the population model, and we are trying to make it more closer to the population from using the sample data using the estimated regression model. And there are different type of dependent variable. One dependent variable is a continuous one, the ratio model, interval, ordinal, nominal. We will see all those things in this particular video. There are three types of fundamental data. One type of data is called the time series data, where the time is changing but the unit of study is like fixed. For instance, here it says that a set of observation that a variable takes a different times. So a specific variable, but there are different time period. For instance, GDP, you can check the GDP over time period. That is called the time series data. Cross-sectional data, on the other hand, there is a specific time period, but the units of study are different. For instance, if you are working for a population sample size where different type of household survey you are doing, that type of study is considered as a cross-sectional data. Panel data combine the time series and cross-sectional concept together, and that is what we say panel data. The method of ordinary least square is the very popular model in linear regression model, and the main idea of the method of ordinary least square is to minimize the sum of squares error, meaning that we would like to minimize the error term as much as possible and try to close to the population model. That is the idea of the ordinary least square technique. And to obtain the values of regression coefficients, derives are taken with respect to the regression coefficients and set equal to 0. Classical linear regression has few assumptions. Model assumption starts with the model should be a linear model, and regressor are fixed or non-stochastic. And also there are some like homoskedasticity, no autocorrelation, no multicollinearity, no specific bias. So those things we will discuss those things. There are two other things that we have to remember. One is called the Gauss-Markov theorem and the other one is the Bayesian model. Gauss-Markov theorem is more or less focusing on based on the mean centric analysis. On the other hand, the Bayesian model more or less discuss about the prior thinking, prior or historical understanding. So estimators or linear function of the dependent variable, the estimates should be unbiased and it gives you a blue result, best linear unbiased estimation result. That is what we call the Gauss-Markov theorem under blue assumptions in ordinary least square technique. So here there is a hypothesis testing, t-test, and as you know there are two types of hypothesis. One is called the null hypothesis and the other one is the alternative hypothesis. There is an example given over here. Normally when we test any hypothesis, t statistics is one of the key criteria that we apply for our hypothesis testing, and here the p-value gives the exact level of significance. Depending on the p-value from 0.05% to 1%, we can say whether the variable is significant or insignificant. Goodness of fit, on the other hand, one of the other criteria to understand the model goodness, and R square is the representation of the goodness of fit, and it also says the coefficient of determination gives the percentage of total variation in the dependent variable that is explained by the regressors, meaning that all the independent variables that is available in your model, how well the model is explained by the regressor, and that is what we call the goodness of fit, or in other words R square. Chapter 2 is basically discuss about the functional form of regression model, and chapter 2 is nothing but to show you that there are a understanding of any regression model, you need to put the functional form. For example, y is equal to function of KL, K here the representation of the capital and L representation of the labor. So if you would like to run a regression based on the output, labor and capital, that functional form can be represented using a linear regression model, and that's what it says in chapter 2. So I skip that part because it is a very small part and you can easily have a look, because I already give you the link of all the slides that I am sharing over here in this particular video. Now chapter 3 is talking about the qualitative explanatory variable in the regression model. Qualitative meaning that the variables are taking either nominal or ordinal values. For instance, if your regressors or the explanatory variable is giving you gender, for example 1 for boy, 2 for girl, something like that, then it becomes a qualitative variables, and qualitative variables are nominal scale variables, and these values are quantifying using the dummy variables taking 0 and 1. Now these variables are also called the categorical variable. Now there is one thing you have to remember is called the dummy variable trap. If an intercept is included in the model, the number of qualitative variables which are m categories, you need to choose the dummy variables depending on the m-1 criteria. This is very important to remember, because without that you will not able to pick the right model for the regression analysis. So it is always remember that you should pick the number of dummy variables or number of categorical variable depending on the categories minus the -1, that will be your number of dummy variables. Okay, and then the next one is the reference category. Always remember that whenever you are running a regression using a categorical variable, you have to consider a reference variable or reference category, in other words. For instance, now chapter 4 is discussing about the regression diagnostic. It is very important, once you run a linear regression, you need to check all the assumptions. Once you check all the assumptions, you are able to say that whether your model is a best fit for your analysis. The first one is called the multicollinearity. And what is multicollinearity? Multicollinearity meaning that the two regressors or explanatory variables will be highly correlated, and that is what we call the multicollinearity. If there are one or more such relationships among the regressor exist, we call it multicollinearity. What will be the consequences? If the collinearity is not perfect but high, meaning that high correlation between the two explanatory variable, the OLS estimators are still gives you the blue result, but one or more regression coefficients have a larger standard errors, and that will gives you a higher R square. The R square might be misleading in this case. So you need to check the multicollinearity in order to get the accurate R square or goodness of fit. Now, to understand the checking of multicollinearity, we use the variance inflation factor. All these simple mathematical terms are explained in the solution manual in a more detailed way. I strongly recommend you to have a look the solution manual. You will get all the answers that is required. But here it is very simple that how to check the variance. Normally, detection of multicollinearity, normally R square but a few significant T ratios. If high variance inflection factor, particularly exceeding 10 in value, then you will say that there is a higher multicollinearity problem exists. Low tolerance factor. So the last point here is the most important thing. High variance inflation factor, particularly exceeding 10 in value, showing the multicollinearity present in your model. What is the remedial measures in this case? The first remedial measure is to do nothing, check the data. And then the next one is to redefine the model by excluding the highly correlated independent variable. And to do that, you can always refer to the principal component analysis. So in this particular video, we are not covering principal component analysis. However, I strongly recommend you first check the data, run the regression. If it gives you higher R square, follow whether the two variables are highly correlated. You can easily do it by just applying the correlation analysis, and if the correlation exists between the two explanatory variables, high correlation, then leave one variable and run the regression without that variable. That will remedy the multicollinearity problem easily. Now the next one is the heteroskedasticity problem. What is heteroskedasticity problem? It actually is showing that one of the assumptions in the classical linear regression model that variance of the error term should be constant. The variance of the error term should be constant or homoskedastic. Reasons are many, including the presence of outliers in the data. Why this problem occurs? If there is a higher presence of outliers in the data, incorrect functional form. For instance, if the functional form is incorrect and your variables are not according to the model that you are looking for, you set it by mistake. In that case, this problem will arise. And also incorrect transformation of the data. For instance, if you are not putting the growth model instead of a raw facts, that will also cause the heteroskedasticity problem. What would be the consequences? The consequences here is that the OLS or ordinary least square linear regression model estimators are still unbiased and consistent, yet the estimators are less efficient, making statistical inference less reliable. In the presence of heteroskedasticity, the blue estimators are provided by the method, the weighted least square. So how to detect that? There are several tests. For example, the famous one is the Bush-Pagan test, White test, and the Park test. And there is also another test called the graph histogram by eyeball method. So here the Bush-Pagan test explained here. In my opinion, if you go to eViews or Stata Help, by showing the Bush-Pagan test, you will find how to check the Bush-Pagan test using eViews, Stata or R. I will recommend another software called the JAPS and Blue Sky Statistics. These two softwares are R-based software. This will also help to identify the Bush-Pagan test. Similar to the White test of heteroskedasticity, and there are simple steps of doing the heteroskedasticity White test given over here. So what are the remedial measures? The first remedial measure is to use the method of weighted least square. In my opinion, WLS is the best way to avoid the heteroskedasticity problem. Another best way is to take natural logarithm of dependent variable. Take all the variables ln before you running any regression analysis. Another important point of the regression diagnostic analysis is called the autocorrelation. In this particular case, autocorrelation shows the relationship between the error term, meaning that the error terms of the observation, it should be no relationship, but over the time it shows that the covariance between the two error terms are related. And that is the problem of autocorrelation. What would be the consequences in this case? The OLS estimates are still unbiased and consistent, but they will still normally distributed in the large sample. In the most cases, the standard error are underestimated. So this is what the problem of autocorrelation. Normally, autocorrelation exists in time series data, as it will fall under the time related issues. So it is more often found in a time series data. One of the important way to detect the autocorrelation is the Darwin-Watson test and Godfrey-Pagan test. So the Darwin-Watson test is very simple. Take the two error terms difference, make it square and divided by the error term, the base error term. What are the assumptions for Darwin-Watson test? The regression model includes an intercept term, and also we will try to see what Darwin-Watson value gives you. You will look at the value at the bottom, where you can find out very easily that the Darwin-Watson test, which gives you the result of 2, close to 2, that will show no evidence of positive or negative first order autocorrelation. So you will find out that if there is a value close to 2, there is no autocorrelation. If it is less than 2 or higher than 2, of course there is a positive or negative autocorrelation presence in your model. In order to avoid that, you can use the Bush-Pagan, the White test, Darwin-Watson test, and also the remedial measure. In order to avoid the whole thing before testing anything, there is a way called the fast difference transformation. Normally in a time series, if autocorrelation presents, we take the fast difference, what we call in short form autoregressive distributed term leg number 1 or difference number 1. So that will keep the autocorrelation minimum, and that will easily make your data and analysis more accurate. Another thing is to keep in mind the model specification error that will arise if you omit an important variable from your model, and that is what we call the model specification error. If we omit a relevant variable because we do not have the data, or because we have not studied the underlying economic theory carefully, or because we have not studied the prior research in the area thoroughly, just due to the carelessness, we will underfitting our model. And that is what we call the model specification problem. The consequence will give you the inaccurate result, and the disturbance term will be inaccurate. The variance of the estimated coefficients of the misspecified, and this sort of problem will start if you misspecified your model. One of the way to avoid the omission of the variables by detecting the omissions of the variables. One of the key application of that called the Ramsey regression specification error or RSAT test. There is another way is called the Lagrange multiplier or LM test. Ramsey test and the LM test are available in eViews and Stata. At the same time, you can apply the R programming by checking the Ramsey test and the Lagrangian multiple test. In this particular study, you will find all the step-by-step information given in the slide, which I already shared in our video description box. You can just have a look. So inclusion of irrelevant or unnecessary variable that will give you higher R square. So be careful. In my opinion, to avoid that, you can use two methods. One is called the forward selection and backward selection. Forward selection meaning that you add few variables and then see how R square react. Backward selection meaning that you drop variables and see how the R square react. If the R square is changing significantly, if you drop or add any significant variable, then only you understand that whether this variable is important or not necessary. So this is what you have. Consequences are serious because the error variance and the specification of the model will be incorrect. It will give you underfitting or overfitting problem. Now, chapter 8 is discussing about the Logit and Probit model. In econometrics or statistics, Logit and Probit model are quite often analysis we apply, especially in a primary data analysis where your dependent variable is a categorical variable. So, regression model involving categorical or qualitative response or independent variable that will gives you the result of Logit or Probit model. The linear probability in this case, the OLS method will determine the probability of an outcome. So, the Logit model comes if the outcome decision or Y variable depends on an unobserved utility index such as 0, 1. In that case, we apply the Logit model. In one way, you can say that if dependent variable or Y is a model of categorical variable, in that case, we apply the Logit model. Remember, my dear learners, in this case, the Logit model explanation is a bit different than the normal linear regression or continuous variable. The most important part over here is the odds ratio. Odds ratio meaning that whenever you are changing any one variable, you have to check the probability of other variable occurring, right? And the similar type of model is called the Probit model, where the Probit models, the main difference between Logit and Probit model are the error term in this case in the Probit model are normally distributed. That is the only difference between Probit and Logit model. The Probit and Logit model is not that difference. You can easily apply any of this model in the case of categorical dependent variable in your model. So Logit versus Probit, there are not generally almost gives a similar result. The main difference between these two models is that the logistic distribution is slightly flatter tails. In practice, there is no compelling reason to choose which one is best. So in my opinion, it is easier. You can choose for Logit or Probit. Now we move to the time series analysis. Time series analysis is one of the important analysis or methodology we use in our data analysis. Whether it is a social science or engineering or any other science, time series is one of the important application of data analysis. In this case, we have to remember most economic time series there are two types. One is called the stationary and non-stationary. Stationary meaning that the average mean of all the time related variables will be the same, whether there is no trend showing, no other randomness or white noise exists in the trend. On the other hand, in the non-stationary, in this case you will find always a trend pattern in your model. Such series exhibit an upward or downward trends over a sustained period of time. That is the main difference between stationary and non-stationary. Normally what will happen, my dear learners, if there is a trend exists, our analysis will give us a misleading result. So to avoid that, we need to remove the trend and make that series a stationary one. In order to do that, the first thing we do is take the first difference. And taking the first difference in the time series model is called the unit root test. So time series plotting is one of the important to check whether the trend is available or not. Autocorrelation function or ACF is one of the other important diagnostic tools to check whether time series is present in the model. If the ACF is over time slowly decaying and there is no result coming at some point of time, then you will say that your time series now become stationary. And as I said that one of the other ways is called the unit root test. In EViews or Stata, the first thing you will do in the time series is to take the unit root and take the first difference whether the variables or the series is non-stationary. To make it stationary, we need to check the unit root test results whether the p-value is under the 5% level of significance. We say we reject the null hypothesis, we accept the alternative hypothesis, meaning that there is no trend showing the main series is stationary one. So that is the first thing you have to do in a time series analysis. And all the steps are given over here very nicely. You can use use stata or R to try unit root test. One of the important tests in the unit root case is called the augmented Dickey-Fuller test or ADF test. You can easily do the test. All the mathematics are not necessary at this moment if you are applying it for a empirical analysis. However, if you would like to more about the mathematical, the explanations are given in the solution manual which I am sharing in this video's description box. In the time series model, co-integration and error correction model is one of the important things. Normally, if there is a two series in time series model and they are correlated in one point of time, then we say that there is a co-integration presence in your time series analysis. Thus, there is a unique case where a regression of a non-stationary series on another stationary series does not result in a spurious regression. If two time series have stochastic trends, a regression of one on the other may cancel out the stochastic trend, which may suggest that there is a long run or equilibrium relationship between them. Keeping in mind that unit root and the non-stationary are not synonymous thing. Unit root and non-stationary are not synonymous. Non-stationary meaning that there is trend presence. Unit root is to test that trend and convert it into the stationary one. So test of co-integration is one of the famous ways called the Engel-Granger test, and this test gives you whether the co-integration presence in the model. And you can do it by applying the EViews or stata or R programming to find out the EG model. You can always write to me for more understanding about the co-integration test. I always get back to you whenever you send me any email or any comment. So the first thing you have to do is to check the unit root test, make it a stationary to stationary one, and then run the co-integration test, EG test, to find out whether the two series are co-integrated. If there is a co-integration possible, there is a co-integration, then there you can apply the error correction mechanism, whether these two changes in the short run and the long run, how well the change is occurring. For instance, in this case, if the two variables y and x are co-integrated, the relationship between these two can be expressed as an error correction mechanism. The ECM postulates that changes in the dependent variable y depend on changes in the independent variable over time, and the lagged equilibrium error term here is mu t minus 1. If this error term is 0, there will not be any disequilibrium between the two variables. In the case, the long run relationship will be given by the co-integration relationship. For a multiple cases, we use the vector error correction model. Remember, my dear learners, VECM model consists of different time series. For example, one dependent variable, several independent variable, and we are combining these two together to run a time series analysis. In this case, we apply the vector error correction model. But for a single node, we don't need to apply vector error correction. Now we move to panel data regression model. In the panel data regression model, these are based on panel data, where it combines the time series and the cross-sectional data together. A balanced panel has the same number of time observation for each cross-sectional unit. And panel data have several advantages over purely cross-sectional or purely time series data. So in the panel data, there are two types of static panel model, fixed effect model and random effect model. Remember, my dear learners, there is a dynamic panel model, and in my channel there is a separate video on panel dynamic model. I strongly recommend you to check that panel dynamic model video to understand the dynamic panel data analysis. I have other panel models and time series model in my channel. I strongly recommend you to check those as well to understand deep into the panel and time series analysis. In this case, fixed effect model, when we have a fixed number of intercept. For instance, the intercept in the regression model is allowed to differ among individuals to reflect the unique feature of the individual units. We allow the intercept to vary. And this is done by using dummy variables, provided we take care of the dummy variable trap. Fixed effect model is appropriate in situation where the individual specific intercept may be correlated with one or more regressor. For example, the population change, okay, in a country, and this is related to your economic growth, okay, or the size of the country or the geographical location of the country is related to the country's economic development or the trade. In that case, the fixed effect model is more appropriate. But it will consume a lot of degrees of freedom, and practically I don't recommend fixed effect model. Rather, we recommend the random effect model. In a random effect model, we assume the intercept value of an individual unit is a random drawing from much larger population with a constant mean. Normally, in the case of random effect model, we choose the intercept of cross-sectional unit is uncorrelated with the regressors, meaning that the population change or geographical location, which is supposed to be not changing over time, this will not affect to your explanatory variable. And that is what we allow, that we are preferring random effect model more in panel analysis. However, whenever we have a undecided whether we apply fixed effect or random effect model, there is a test called the Hussman test, and we apply this Hussman test to find out whether we choose random effect or fixed effect model. In the case of Hussman test, we can apply the stata eviews R to check whether the Hussman test chi-square value are within the range of 5% or 1% significance. Finally, we have come to the end of the video, and I am thanking you whoever coming to this far. It means that you are very eager to learn the econometrics. Please feel free to comment on this video and also send me an email to understand econometrics in more detail. You can have these slides and notes and solutions by my video description box link, and you can go one by one. So the last part of this video is called a method of instrumental variable. Stochastic analysis or any regression analysis, there is always a chance of a endogenous problem. Endogenous problem occur when your regressors or explanatory variable are related to your error term, because you know that an error term should be uncorrelated with your explanatory variable, meaning that your independent variable. But if they are correlated, we call such regressor stochastic or endogenous regressors. In this situation, the OLS estimators are biased, and the bias does not disappear even if the sample size increases. In my opinion, the more sample size will give you the accurate results, but in the case of the regressors are correlated with the error term, that gives you biased results in the model that you are analysis. So it is always remembered that whether your error term and the regressors it should be uncorrelated. Now, reasons for correlation between the regressors and the error term. Number one is the measurement error in the regressor. Maybe you are choosing a variable that is more correlated. For example, in one single model, if you are choosing trade openness and FDI together, there is a high chance these two independent variables are correlated with the error term, because these two are representing the same thing. In this case, you choose one over other, or you choose one variable to understand the relationship between the dependent variable. Otherwise, both the variable, one of these may be related to your error term, and that gives you an endogeneity problem, and that will create a misspecification of your model. So To avoid that, we use the instrumental variable that is called the proxy variable, which can give us a consistent estimators of the coefficient of the suspected stochastic regression. For example, if you are finding a variable that is related to the error term, instead of using that particular variable, use a proxy variable that can be related to your suspected variable. At the same time, it is uncorrelated with the error term, and that's what it says. It must be uncorrelated with the error term, correlated with the stochastic or suspected regressors, and not regressors in their own right. So taking the instrumental variable is very tricky, and it depends on the theory and the context of your analysis. You have to study the literature review to pick the right instrumental variable for your model. Without the right instrumental variable, you will fall under the problem of misspecification bias problem in your model. So taking that, it is always remembered that in the large sample, the instrumental variables are normally distributed with mean equal to the true population. This should be the characteristics. But in a small sample size, instrumental variables are biased and their variance are less efficient than the OLS estimators. The success of the instrumental variable depend on how strong they are related to your suspected independent variable. So instrumental variable or the proxy variable must be strongly correlated with the stochastic regressor that you are omitting. If this correlation is high, we say such instrumental variable are strong, but if it is low, then we say weak instruments. As I told you that it is always consider your context and the theory where you are applying and choosing the right instrumental variable. To pick the right instrumental variable, I always recommend to study the literature and then you choose the right instrumental variable in order to avoid the relationship between the regressor and the error term and avoid the endogeneity problem at the same time in your regression model. So that will end up our understanding of the basic regression model is diagnostic, panel, time series and instrumental analysis. In this whole video, I am trying to give you a snapshot of all the models available in regular regression analysis. You can apply any of this model under your context and your analysis, and you can always choose the right model by discussing or referring to these particular slides and their solution manual of the book to understand more detail about the econometrics. I believe this video will be useful because all the statistical models that will be useful for any type of analysis are given in this particular video. In the next video, we will discuss some other models in more detail. But until then, see you in the next tutorial with more exciting research related topics. Thank you, my dear learners. Thank you so much.